Alright, so in this problem we have this box. We release it from rest. It starts sliding down this hill. At the beginning of the hill, or at least the beginning of its slide, there's no friction. And then after sliding some distance, then we have this sort of shaded region here where we do have friction. So the block slides down and then it hits that friction area and then comes to a stop. At least for block A, it comes to a stop down here. And when we repeat the experiment again with another block, the exact same mass, let it go. It comes down, slides, and then hits that friction and stops right there. There's block B. So what I want to do is plot S. Here's S, right? The distance the block has traveled. So I want to make a plot of S as a function of time. I also want to make a plot of S dot and S double dot as functions of time as well. Now I'm not asking you to make quantitatively precise plots here. I just want you to get shapes on the screen or shapes on your paper that represent the basic features of this phenomena. Now what students are tempted to do always, at least when they first see this, is just start from the S and then start drawing something that seems right to them. But remember, seems right is not what we're after. We're after something more rigorous than that. What we'd like to do is connect this up to the physics of the problem, not connect this up to our intuition, not connect this up to our sort of our gut feeling or our hunch of how these plots will work, but actual physical rigorous justification for how we draw these plots. So we're looking for some sort of analysis without equations again. All right, so we want to connect this to the physical principles. So let me scroll back up to the top, and then we'll get to it. So what do I know about this block physically? Well, I know there's forces on it, right? There's gravity tugging it down. I got a force from the ramp pushing it up, keeping it from penetrating the ramp, right? So let's start drawing this free body diagram. I'll abbreviate it FBD. And again, on the free body diagram, go forces. We'll start by adding that weight in here. Weight is vertically downward, like so. This is equal to m times g in the minus j hat direction. And then there's the normal force, right? The normal force is perpendicular to the ramp. It's the force that keeps the block from falling through the ramp. And it's right here. I'm going to call that n. And what else? While we are on this top part right here, where no friction is, that's it. Right? I don't have anything else. Just the weight pulling down and the ramp pushing back up. Right? A little later on we'll add the friction in, but for now this is all we have. Now recall when we were back doing statics problems, what we said is we sum up all the forces and we added them to 0. Right? So all we really cared about these forces and adding them to 0, I guess. But these forces were the main things we worked with, right? In statics. Right? And that's why we had this free body diagram, so that we can sort of graphically or diagrammatically depict all the forces acting on the body. Now in dynamics, once things start moving, in particular when things starts accelerating, we've got some more interesting things going on. In that case, the forces do not add up to 0 anymore. The forces instead produce acceleration. So I got F equals ma. Now on the left-hand side we have all these forces. There's our free body diagram. On the right-hand side we have this inertial piece. Mass times acceleration. So, in addition to the free body diagram represents the left-hand side of the equation, we're also going to have what I call the mass acceleration diagram. That is the vectors on the right-hand side of the equation. So for the mass acceleration diagram, I tend to abbreviate that MAD. What I do, again, I put the right-hand side of Newton's second law in there. So mass times acceleration. So we've got this block and it's moving along a straight line. And we've seen in our studies so far that when we're moving along a straight line, that acceleration has to be along that straight line. It can be in the direction of motion or it can be in the opposite direction of motion, but it's in that it's aligned with that direction of motion. So I'm going to draw that mass times acceleration vector right here. And there's my mass acceleration diagram. Again, this vector is aligned with that ramp. And when I label this vector, remember I have to label mass times acceleration vectors just like I label force vectors. I'm going to use some quantities of interest to us. Well, in particular, we're given this distance of the block travels s, right? And s dot would be its component of velocity. And S double dot, the other thing we're trying to plot over here, that's an acceleration, right? Or a component of acceleration. So I'm going to write this acceleration here as ma s double dot, and I'm going to put, it has to be a vector. Then I'm going to call this e hat t. So ms double dot in the e hat t direction. What's e hat t? E hat t will be a basis vector that's aligned with the ramp, so it's tangent to the ramp. And then I'll pick e hat n to be the direction perpendicular to that ramp, right? So my acceleration, again, is in the e hat t direction. And there's my mass acceleration diagram. All right, now that I have these two diagrams, it's time to connect them together. And they're connected together through this F equals ma. And of course, F equals ma is what we know, or what we call Newton's second law. It simply states that all the force vectors, take all the force vectors, add them together, and that has to be equivalent to our mass times acceleration vector. So these two forces have to add up to that thing. Now, how are these two forces, which are not in the e hat t direction, going to add up to a vector in the e hat t direction? Well, the best way to see that is to put these two vectors into this set of bases here. So in other words, do a force decomposition. For the normal force, that's easy because the normal force is already in the e hat n direction, right? That's already in the e hat n direction. I don't have to do anything special to that one. But the weight, it's straight down. And to put that into this sort of tangential and normal directions, again, it's just a vector decomposition. And if I were to call this angle down here theta, then this piece in the e hat t direction, that would be an mg times sine theta, and the piece in the minus e hat n direction, that'd be an mg cosine theta. But now we're at the stage where you can ask, well, how can these vectors, the weight and the normal force, add up to something in the e hat t? Well, I'm hoping it's quite simple right now. The way it works is that this normal force has to exactly balance the e hat n component of the weight, right? This has to exactly balance that. These two pieces, this one going in and this one pushing out, those have to exactly cancel each other out, just leaving this one little piece right here remaining. And that's the piece that's going to create this mass times acceleration. And if you haven't noticed it yet, this is rather profound. It's saying that this acceleration has to equal this part of the weight, this tangential part of the weight. And guess what? This potential part of the weight's constant. So we know a lot about the acceleration. So we should not be starting or drawing our pictures about the position or the velocity. What we know about from the physical principles of this problem is the acceleration. So don't start with this graph right here. Do not start with this second graph either, because that's velocity. What we know about is acceleration, s double dot. Okay, so this is where we begin plotting things. And what is s double dot? S double dot, m times s double dot equals m times g times sine of theta, right? It's this component of my weight. And this component of my weight, what do I know about it? Right? It's there because I have some weight, but the total weight's not changing, right? So that part's constant. I have this particular component because of the slope of the ramp at some angle theta, but the ramp is not changing its slope. It's not changing this angle either, right? So this component of the weight is constant. The entire time this block is slowing down, that component of the weight is remaining the same. So if this component of the weight's remaining the same, then the acceleration has to remain the same, right? This component of the weight's pushing down the ramp in the direction of positive s, so s double dot has to be positive. Wow. That tells us a whole lot, actually. So we're going to cruise down here. We're going to find s double dot. This is, I'm not sure if it's so visible on your screen here, but that's s double dot. And what we know is while the block is on this portion of the ramp without any friction, in other words, when the free body diagram looks just like this, then we know s double dot is positive and it's constant. So let me draw that. So the first portion of our journey here, s double dot positive constant. Wow. Now we have something rigorous. So now that I have this acceleration, I can start plotting velocity and position now, right? It's just integrals. They're related to each other by integrals. At least I can do it while the block is still in this non-friction part of the ramp. So let's just begin this. So if s double dot positive constant, what's s dot? Well, it's going to have positive slope, right? And I told you that this block starts from rest, so at time equals 0, it's not moving, which means S double dot starts off right here at 0. And then this positive acceleration, what that means is that my velocity has to be increasing linearly until that time that we get the friction. So there's my S dot. My S itself, I have to integrate the velocity to get position, right? I start off at S equals 0. So I'm starting off right there, and I'm integrating this thing. And what does that look like? It's starting off at 0. Since velocity at 0, that means it has to start off with 0 slope, so it has to come off that 0 like that. And then the slope is steadily increasing. So it starts off with 0 slope, but that slope is gradually increasing. In other words, this curve is gradually getting steeper. And I'm realizing that I'm not leaving enough room to fit the rest of this thing. So let me bring it back and then come off a little shallower, maybe a lot shallower. Anyway, something that looks like this. It should be, technically, since this one's linear, this one should be parabolic. But it starts off with 0 slope, and its slope is steadily increasing, like so. So there's my position, velocity, acceleration plots in this first part of the interval right here, right? Oops, this part, up until we get to where we have friction. Next, what we need to do is look at what happens when we add the friction in. All right, so the next thing we need to do is add friction. And since friction is a force, we need to put that friction onto the free body diagram. So I already have a free body diagram over here without the friction. Let me just draw another free body diagram, this time with friction. So I'll label this one FBD as well. And here we have our weight again. We have the normal force again. Again, the weight can be split into two components. So right now the free body diagram looks exactly as it did before. What we're doing now, the thing we're doing differently is we're putting in the friction force. Friction force is at the surface where the block meets the ramp. So it's down here. And which way does the friction act? So the block is sliding down, and friction tries to oppose the sliding. Right? It doesn't like the sliding. It resists the sliding. So since the box is sliding down on the ramp, the friction is going to be pushing up against the sliding, against the motion of the block. So I'm going to draw the friction right here, something going up, something tangent to the ramp, right? So it's going to be I'll call it F in the minus E hat T direction. And I might be getting into my place where I'm going to plot my position, but that's okay. So there's my friction force. Now the mass acceleration diagram, it's still the same, right? Nothing has changed. This thing's still moving along a straight line, which means this acceleration must be in the direction of that straight line. So it's tangent to the ramp. Now it might actually point backwards, but it's still tangent to the ramp. So this expression for a mass acceleration diagram, I think, is just fine. All right, but now what's producing the acceleration, again, look at these. Now I have three different forces: weight, friction, normal force. All three of those have to add up to something along this line. So what we have is exactly, at least part of this, what we have is exactly the same as we had before. In the normal direction, I've got this normal force, and I've got this part of the weight. Those are the only two pieces in the normal direction. So again, these two pieces have to exactly cancel each other out, right? The normal force and that normal component of the weight have to cancel each other out, add up to 0, because there's no acceleration in that normal direction. So what we do, what we look at, what we have left is again this component of the weight right here. That tends to push the block down the slope. But we also have this friction force right here as well, and that's pulling up. So these two forces are going against each other, right? They're going against each other. So when they add up to something, they're going to add up to something in this direction. But depending upon which one is bigger, it's going to tell you whether this acceleration is positive, which means down to the right, or negative, which means up and to the left, right? Which one is it? Do I have a positive acceleration or a negative acceleration? Let's think about that for a second. Well, it actually, the clue for which one it is comes from the statement of the problem, right? The problem states that the block is released from rest, it keeps on sliding down, hits the friction, and by the time it reaches point A, it comes to a stop. If it comes to a stop down here, that means the velocity should be decreasing in that friction zone, right? Velocity should be decreasing in that friction zone, which means, where'd the velocity go? Remember, velocity was increasing, and then it has to decrease. If velocity is decreasing, then the acceleration should be negative over here, somewhere in the negative regime. Let's look at that acceleration. So what this is telling us is that this friction force has to beat out the tangential component of the weight, right? The friction force has to be bigger. But can we find out more about that friction force? First of all, is it something that changes in time? Does that friction force get bigger or smaller as the block slows down? To answer that question, let's go back to the Coulomb model for friction. The Coulomb model for friction tells us that friction magnitude is equal to while the block is sliding, is equal to mu k times n here, where n is the magnitude of the normal force, right? So there's the magnitude of the friction force is equals mu k times n. So there's our model for friction, at least of how friction works. Notice that the friction does not depend on velocity. What friction depends upon is the normal force. That's the force pushing these two surfaces together. The bigger the forces or the surfaces are being squeezed together, the more friction, the more normal force, which means the more friction. But let's look at this normal force. Remember, the normal force, what that does is it balances this component of the weight. This component of the weight's constant, right? Because the total weight is constant, and the block, or at least the ramp, is at a constant angle. So this angle right here, this is not changing in time. So therefore, this normal component of weight must be constant, which means my normal force must be constant, which means my friction must be constant, which means since these two forces add up to my acceleration must be constant as well, right? So there's a lot of things going on there to tell you that the acceleration in this, after we get to the friction, is constant. Whew, that was a mouthful. So in the end, what we know is that this acceleration has to be constant, has to be negative, so I get something that looks kind of like that for my acceleration. Yes? All right, so now that I have this negative acceleration here, that means my velocity must be decreasing linearly. So I'll draw that like so, which means, what does that mean for position? So it starts off with zero slope, right? So it slowly gains slope. And then what happens after we hit the friction is we start off with the slope at this, we have a speed at this speed indicated right here. So right after we hit the friction, this is nice and tangent right here, but the slope is going to start decreasing. So I'm going to get a parabolic sort of behavior this way up until the point at which we stop, which is probably right around there. Yeah, so there's position. Here's velocity, and finally, here's acceleration for block A. The plots for block A are done. All right, now I think the only thing we have to do left is discuss block B. Remember, what happens with block B, it has the exact same mass as block A, but when we let it go, it picks up speed, and then once it hits the friction, it comes to a stop right here. Doesn't slide quite as far as block A, right? So let's draw the position, velocity, acceleration plots for that thing too. Now, so what's the difference between block A and block B? Let's look at this part where we're not on the friction first. Both blocks have the same mass, so block A and block B will have the exact same mass vector, the exact same component in the direction of travel, so the E had T direction. It's this component of your force that's producing acceleration. Again, mass is the same, so it should have the exact same acceleration. So therefore, block B will have the exact same acceleration. I'm just going to sort of draw it over this one right here. Again, the exact same acceleration while we're on the non-friction part. When there's friction, what's happening? After there's friction, this block is slowing down more, or slowing down faster. So what that's telling us is that this friction force has to be bigger. Right? It's the friction force that's slowing down. It's not this weight right here is not changing. This component of the weight, that doesn't change. It's the friction force. This is the only thing that can change. Notice that the normal force didn't change, right? Because the normal force balances exactly that component of the weight. Normal force didn't change. What must be different, since the friction force is different, is that friction, that coefficient of kinetic friction, UK, must be bigger, right? So that means that this acceleration must be more negative, and of course it's still constant because it's that friction force is mu k times the normal force, and the normal force isn't changing anymore. So here's what I have for my acceleration after we hit the friction. Now if we go back up here, again, since the accelerations are the same, block B will have the exact same velocity profile for this first part. However, it will decrease speed considerably faster, and I'll get a velocity profile like this. In other words, speed decreases a lot faster. The block comes to a stop a lot sooner. And maybe I should continue on here. Once the block comes to a stop, it stays there, right? Ooh, maybe I got something wrong with my graph here. Once it comes to a stop, it has to stay here. It just stays put. So my velocity graph goes like this. So after it comes to a stop, I get velocity hits 0 and stays 0. So really what should be happening with my acceleration plot over here, my acceleration is quite negative until right here where it jumps back over to 0. I've got no acceleration, no velocity. The block is perfectly stationary again. So again, blue one jumps this way and then jumps back, or excuse me, the green one, block B, jumps this way, jumps back, like so. And now I just have to integrate position. Again, the block A and block B are identical until we hit to the friction, which is about that time right there, where this peak is. And then what happens is velocity goes to 0 faster, which means that the position curve flattens out sooner, and we get something like this. In this part of the plane where we have zero velocity, the position should be constant. The position is not changing. So I'm thinking my position curve for my block B looks something like that. Woo! And I'm done. You might ask, what's going on when block B stops? When block B stops, what's going on with the free body diagram? Well, when block B stops, we don't have the sliding friction anymore. We don't have a friction which is proportional to the normal force. What we have instead is a friction force which exactly balances out that component of the weight to give us 0 acceleration. So the friction force gets quite a bit smaller as soon as the block stops. And that's it. Story finished.